In the previous lecture, we stopped with a small brief discussion of current mirror circuits. So, in this lecture, we are going to take that forward to see a few different types of current mirrors. So, first we will start off by drawing the basic current mirror that we looked at in the previous class. So, if you take a current I naught and pass it through a transistor with a certain width over length, this will generate through a feedback action, this will generate a voltage VGS. I will call it VGS1 and I will call this transistor M1. This will generate a voltage VGS1 that will correspond to a drain current of I naught. So, this will clearly be Vt plus Vd sat at a current I naught. This is nothing but Vt plus this will be the voltage generated. Now, this voltage can now be applied to a second transistor, which will now have a current, a drain current that is related to the gate source voltage as half mu n C ox W over L into VGS1 minus Vt the whole square. Now, if you ignore the dependence of the drain current on the drain source voltage, this will clearly be equal to I naught. Now, this assumes that the drain source voltage for the second transistor is large enough such that it is in saturation. So, this assumption is made. The transistor M1 is always in saturation because the drain voltage is equal to the gate source voltage. So, this was the simple current mirror we saw last time. Now, this current mirror can be used to bias other circuits. For example, this portion of the circuit looking down looks like a current source with a very large resistance. The value of the resistance is the output resistance of the MOSFET, which is RDS2. So, this transistor M2 to the rest of the circuit presents itself as a current source with some RDS2. So, if you want the bias circuit to look ideal, if you want it to look like an ideal current source, you need to make RDS2 as large as possible. So, this is going to be one of the design constraints. Now, normally RDS2 of course depends on the bias current, but since we are constrained to have a bias current of I naught, RDS2, large RDS2 also means large length, because as it turns out, the longer the transistor is, longer is the length L, larger will be the RDS2, but there is a certain limit beyond which you cannot increase RDS2. Suppose I want to get even better output resistance. So, you want to get a current source which has as large an output resistance as possible. So, that is our goal. So, we now want to make RDS2. Now, with a single transistor there is only so much you can do with RDS2, beyond that you cannot increase RDS2 any further. So, we want to look at circuit methods to increase RDS2. So, one way to do that is to use a different circuit technique. Now, to do that, let us start by adding a resistance R in the source path of the transistor M2. This was VGS1, which is the same as VGS2. I am going to add a resistance R in the source path of M2. I now want to find out what the output resistance is for this particular configuration. So, let us assume that the transistor has a GM and an RDS. So, now to find out the small signal output resistance, I will draw the small signal equivalent circuit. VGS1 is generated by the current mirror, the mirror portion, the left side portion of the current mirror, that will be at signal ground. I am going to call this voltage Vx, so that this current source is going to be at Gm times 0 minus Vx. I want to find out the output resistance looking in from the drain of the transistor M1, and the way I do that is I am going to connect a test voltage V test, a small signal test voltage, and I want to find out what the current drawn by the circuit is, so that my small signal output resistance can be calculated, which is also the Thevenin resistance, can be calculated in this form as V test by I test. Now, to do that, so I am going to notice several things. I am going to note that the current I test flowing in is going to split into two paths in this way, and eventually is also going to flow through the resistance R. So, clearly the current flowing through R is also I test. So, I will point out that is equal to I test times R. Then I will perform KCL at the two nodes to figure out what the relationship is between Vx, V test and I test. So, I am going to perform KCL at the drain node. Those of you who have seen the voltage controlled current source or a source degenerated circuit will know this expression already, but I am doing this for the benefit of all the others who have not seen this circuit before. So, the current flowing in is I test, that splits as V test minus Vx by RDS, that is the current flowing in the right side portion of the circuit, plus minus Gm Vx. So, now I am going to write, for ease of writing the equations, I am going to say that RDS is 1 over GDS, so that I test can be written as GDS times V test minus GDS times Vx, and I am going to write it in this form. Vx I am going to replace with this expression, and now I am going to group together all the terms of I test on one side I am going to write the slightly simplified version as we go along, plus in other words, this R out expression is nothing but small rds plus capital R plus GM rds times R, and as you can see, this is the dominant term, is since GM rds is the intrinsic gain of the transistor, this is the dominant term among all of these terms, and I will write this as approximately being equal to GM rds times R. So, note that if I add a resistance looking in at the drain, if I add a resistance at the source, the impedance looking in at the drain is a magnified form of this resistance. So, now I can of course use this because I can now create a current mirror in this form. I will need symmetric circuits on both sides. So, I will need to add the resistance R on both sides. If I do this, I will, earlier the resistance was RDS, now I am going to write it in terms of the earlier resistance. I will get an output resistance which is equal to GMR times RDS, which hopefully will be larger than RDS itself. So, now I have managed to create a current source. Remember that this current is also I naught. I have managed to create a current source which will have a much larger output resistance. But there is one problem. The minute I put in a resistance here, the voltage drop across the resistance is the DC voltage drop across the resistance is equal to I naught times R. So, if I try to get very large output resistance by increasing the value of R, the voltage drop across the resistance also increases, and eventually what will happen is that the minimum value of VD2 will get affected, because as VR increases, VGS1, or rather I am going to call it VG1, the gate voltage, is equal to I naught R plus VGS1. Note that I have a voltage I naught R here and I have a voltage VGS1 here. So, at the gate of M1 and M2, I will have a voltage which is I naught R plus VGS1, and therefore, the drain voltage can only have a minimum value of VG2 minus VT, i.e. it is VGS1 plus minus VT. In other words, this is the minimum value of VD2. What was the earlier value of minimum value of VD2? In the earlier circuit, the minimum value of VGS1 was VGS1 minus VT. Now, you have an extra term I naught R. So, clearly what is happening is, it looks like a better current source, but now the voltage compliance at the output has now gotten worse. So, I cannot arbitrarily increase the resistance R, I need to find out a different way of doing this. So, now I want to get a large resistance R. So, the next question is, instead of using a physical resistance R, why not use a drain source resistance of a MOSFET itself? In other words, I am going to use the small signal resistance, drain source resistance of the MOSFET to generate this R. Hopefully, in DC it will look better. Let us look at this. If I look at this R out of this circuit, this is clearly going to be GM RDS times RDS, which is going to be very large, hopefully much larger than the earlier number. What about the voltage here? All I have to ensure is that this lower transistor here, now let me name this M3, this was M2. All I have to do is I have to ensure that this transistor has a voltage equal to VD sat, which is VGS3 minus VT. If I ensure that a voltage VD sat is maintained between the drain source of M3, I am assured that M3 is in saturation, and therefore it will have an output resistance of RDS. The small signal model will be valid. So now I am going to draw the rest of the circuit, because we have not shown M1. This is M1. Now note that I need to generate a voltage for M3, and I am going to generate that using a fourth transistor. I am going to call it M0, since it is on the left side. Now I still need to connect the gates, the common gates of M0 and M3 to some node, and this happens to be a convenient node. So now I can calculate what the voltages are in the rest of the circuit. So let us quickly do that. I am going to do the analysis for it here, up here. So note that VGS naught, I am going to assume for this, I am going to assume that all transistors have the same width and length. So note that VGS for all transistors 0 to 3 is nothing but VT plus VD sat 0 to 3. This is VT plus root of 2 I naught over mu n Cox W over L. Since all transistors have the same bias current, this and the same width and length, this VGS will be valid for all transistors. So now I need to find out what the bias voltages are in the different parts of the circuit. So clearly the output voltage is some drain voltage is some VD2. Now I will denote this voltage by VD3, this voltage by VG0, and this voltage by VG1. And I am liberally going to use the term VD sat, because that is much easier to use instead of writing the current expression in terms of currents and mu n Cox. So the first thing I can write is VG0 is equal to VGS 0. Okay. So the gate of M0 and the gate of M3 of course then are biased at a voltage VGS 0. So this is VT plus VD sat. Now VG1, which is the gate of transistor M1 here, is at a voltage of VG0 plus VGS1. In other words, it is biased at VGS0 or 2VT plus 2VD sat. What about VD3? The VD3, the voltage at the drain of M3 is going to be biased at 1 VGS2. So I am going to find out VG1 and then subtract VGS2 from that. That will give me VD3. So note that from KVL, VD3 is equal to VG1 minus VGS3, and this is equal to VT plus VD sat again. Okay. So, in other words, the voltage at the drain of M3 is at a voltage not Vd sat but Vt plus Vd sat. So, it is at 1 VGS above ground. Now, if I start reducing the voltage at the output, let us see what happens. I am just going to look at the output nodes. So, I am going to start reducing Vd2 and if I do this, note that the voltage at the gate of M2, which is Vg1, does not change, the voltage at the gate of M3 does not change, and because M3 and M2 are carrying a nominal current of I naught, the voltage at the drain of M3 also does not change. So, please note that if I start reducing Vd2, as long as the current does not change by a large amount, Vg1, Vg0 and Vd3 do not change. So, eventually the minimum value of Vd2 is clearly Vg1 minus Vt or 2 Vt plus V2 Vd sat minus Vt or Vt plus 2 Vd sat. This is the minimum voltage possible at the drain of M2 before M2 goes into the triode region. Once M2 goes into the triode region, you are not assured that the output resistance is still very large. Please note that the output resistance will be large only if all transistors are in saturation. Now, we have seen that Vd2 minimum is Vt plus 2 Vd sat, but note that M3 still has a voltage Vt plus Vd sat across it, and actually M3 can be in saturation even with a voltage of just Vd sat across it. Therefore, I should be able to push down the voltage compliance of this current mirror even further. I need to do it by changing the bias voltages in the circuit. Clearly this voltage Vg0 cannot be changed because I require that to support a current I0 in this circuit. However, the only way Vd3 can be reduced is by reducing Vg1. So, I need to find out a different way of producing Vg1. Clearly, my original method of making this connection, these two connections may need to be changed because I cannot afford a voltage of 2 Vt plus 2 Vd sat at the gate of M2. So, we come to the final very often used circuit, which is called the high swing cascode. So, this note that this connection, this circuit is called the cascode current mirror. The configuration where you have one transistor stacked on top of another in this configuration is called a cascode, and this circuit is called a cascode current mirror. The next circuit we want to look at is what is called a high swing cascode. Clearly, we still need the stack of two transistors on both sides to generate the large output resistance. However, I want to change the bias voltages at these two nodes. So, the first thing I need to do is I want this to be biased low enough such that the drain source voltage across M3 is only equal to Vd sat. Number 2, I want a current I0 to be drawn from the output. So, I want good mirroring action. I want Vd2 to be as low as possible, to be able to swing as low as possible. So, to do that we are going to use a different feedback connection. So, if you make this connection, this will ensure that this voltage Vg0 will still be equal to Vgs0. So, this is also a case of negative feedback, just like the original current mirror. This voltage will be equal to Vt plus Vd sat. Now, we still have a problem of generating this voltage, which is Vg1. So, the way we do it is we will use a third or a fifth transistor to generate this voltage. I am going to call this W over L of M4, W over L4 for transistor M4. Now, we know the condition now. So, we wanted Vd3 to be Vd sat, so that transistor M3 is exactly at the edge of saturation. We want, therefore, we want Vg1, which is this voltage. We wanted the gate of M1 and M2 to be at a voltage equal to Vd sat plus Vgs2. In other words, this should be equal to Vt plus 2 Vd sat. Note that Vgs2 is Vt plus Vd sat. And if this happens, the drain of M0, which is I will call Vd0, Vd0 will be equal to Vg1 minus Vgs1, and that will also be biased at a drain voltage of Vd sat. What about the size of M4? We will size M4, we will choose W over L of M4 such that Vg1 is equal to Vt plus 2 Vd sat. So, I am going to write down the relationship for M4. So, Vgs4 is note that M4 also has a bias current of I0. This is the current voltage relationship for M4, and note that we want Vg1 which is equal to Vgs4. Please note that in the previous connection this voltage Vg1 is the same as Vgs4. So, we want Vgs4, we want Vg1 to be Vt plus 2 Vd sat. And what is Vg1? Vt plus this is the expression. So, now if Vg1 is the same as VGS4. I am sorry, I have missed a 2 number here. This implies that this means that W over L of transistor 4 is going to be 1/4 the W over L of the other 4 transistors 0 to 3. Okay. So, now the design condition is clear. If you have a current I naught here, if you have a current I naught flowing through M4, the size of M4 should be 1/4 the size of the other 4 transistors. If you do that, the voltage generated at the gate of M4 will be exactly equal to Vt plus 2 Vd sat, and if this is done, Vd2 minimum in such a condition, Vd3 will be equal to Vd sat, Vg1 is Vt plus 2 Vd sat, so Vd2 minimum, that is the minimum voltage possible at the drain of M2, is 2 Vd sat. In other words, you have now managed to bias the transistor such that each of these M3 and M2 can have a voltage of only Vd sat across it and still be in saturation and support a current I naught, and finally have an output resistance which is equal to Gm Rds squared. So, this is a very commonly used current mirror. It is called the high swing cascode current mirror.